Some of the hardest problems in pure mathematics look simple at first. Imagine holding a pen and slowly turning it so it points in every direction. How much space does the needle need to turn? Your first guess might be that it sweeps out a solid sphere, but over a century ago, mathematicians discovered this simple puzzle actually reveals the strange behavior of high-frequency waves. This turned it into a major research quest. In February 2025, a paper appeared on arXiv that solved the three-dimensional Kakeya set conjecture. The proof Wang and her collaborator Joshua Zahl posted was titled Volume Estimates for Unions of Convex Sets and the Kakeya Set Conjecture in 3 Dimensions. Within days, mathematicians everywhere realized the significance of their work. The impact was so strong that MIT's Larry Guth wrote a 21-page survey to help others understand the proof. By January 2026, Guth, Wang, and Zahl released a shorter 47-page version to make the main ideas easier to follow. Nets Katz, a mathematician at Rice University, said, "This thing doesn't need hyping up." Eyal Lubetsky, chair of mathematics at NYU's Courant Institute, called it one of the top mathematical achievements of the 21st century, and the Institute for Advanced Study noted the problem had eluded some of the greatest living mathematicians. Put simply, the theorem says that any Kakeya set in 3-dimensional space, meaning any set that contains a line segment of length 1 in every direction, must have both a Minkowski dimension and a Hausdorff dimension of exactly 3. Wang and Zahl proved that there is a strict mathematical limit to how small a pattern can be when you rotate a one-dimensional segment, like a pen, in every direction within a 3-dimensional space. Experts agree this is truly a once-in-a-century proof. The 3D case is far more important than the 2D case, which was solved in the 1970s, because adding a third dimension brings much more complex geometry, especially with skew lines. In 3 dimensions, tubes can point in many directions and still overlap in complex ways, allowing them to pack much more densely than on a flat surface. The breakthrough quickly made Hong Wang, its young author, one of the most promising mathematicians of the coming decades. She was already well known, having won the 2022 Maryam Mirzakhani New Frontiers Prize for her work in restriction theory and local smoothing conjectures before solving the Kakeya conjecture. But the 2025 proof took her to a new level. After publishing it, she received the 2025 Salem Prize, the 2025 Ostrowski Prize, the 2025 ICCM Gold Medal, and the 2026 Association for Women in Mathematics Sadowski Prize. She is widely regarded as the leading contender for the 2026 Fields Medal, the closest thing mathematics has to a Nobel Prize in July 2026. There is no official shortlist for the Fields Medal, and the International Mathematical Union keeps its decisions secret, so any talk about the prize is just speculation. But Wang's acumen, which combines a rare mix of intuition, persistence, and technical know-how, makes her one of the most deserving candidates.
Solution to the Kakeya set conjecture in R3, we used heavily his discretized sum product.
You might be wondering, doesn't the long-standing focus on a spinning needle seem strange or even pointless? Why spend so much time and effort on it? Who cares? The reason is that the Kakeya conjecture, in fact, forms the foundation for a whole series of important problems in harmonic analysis. The saga began in 1917 when Japanese mathematician Soichi Kakeya asked his original needle question. Imagine rotating a needle in every direction. You might think the needle would cover a solid ball of space in 3D or a circle in 2D. But mathematicians found a surprising trick. By moving the needle in careful sliding steps, you can create a set that is incredibly thin. While the original 2D volume question was famously answered by Abram Besicovitch in 1928, who shockingly proved the area could be pushed arbitrarily close to zero. Mathematically, it is possible to make a shape with zero volume that still contains a line segment pointing in every possible direction. Over time, the focus changed from volume to dimension, leading to the concept of a Kakeya set. In higher mathematics, volume and dimension mean different things. Volume is just the amount of space an object occupies. Dimension, like Hausdorff or Minkowski dimension, describes how complex or rough a shape is, or how it scales. To picture fractal dimension, think of a block of Swiss cheese or a sponge. You can keep making tiny holes until almost no material remains, so the volume is small. But the sponge still stretches in 3 directions, length, width, and depth, so its structure is still fully 3D. The Kakeya conjecture says that even if a Kakeya set is built in such a tricky way that it has zero volume, its fractal dimension still matches the full dimension of the space. In 3D, that means its dimension is still 3. This is the heart of the paradox that Wang and Zahl solved. A shape can have almost no volume, but still keep its full fractal dimension. This question became central because researchers saw it as the base of a tower of conjectures. The Kakeya conjecture is the foundation, with the restriction conjecture above it, then the Bachner-Riesch conjecture, and finally the local smoothing conjecture at the top. Each of these big conjectures depends on the one below it. If the Kakeya conjecture had turned out to be false, if there was a super monster counterexample in 3D, the whole structure of theories about wave equations and the Fourier transform could have fallen apart. Wang and Zahl showed that in 3D, no matter how cleverly you arrange your thin needles to overlap, the resulting fractal shape still has 3 dimensions. It seems strange, but it is true. You can make a cage with zero volume, but it will always be 3-dimensional. Now that the Kakeya conjecture has been proven in 3D, many other tough questions above it seem much more likely to be solved.
It's not just about the solution, it's more like how different parts of mathematics fit together.
Wang was born in 1991 in Guilin, a city in China's Guangxi region, known for its lush, surreal karst mountains. The landscape is so beautiful that a famous proverb says, "I'd rather be born in Guilin than be a god." Raised in a household with parents who were both secondary school teachers, she skipped multiple grades. By the age of 16, she scored a 6.53 on the grueling Gaokao exam, China's equivalent of the SATs, and placed her in the top 1% or higher of examinees in her province, and entered the prestigious Peking University, or PKU. But she did not follow the usual path of Chinese International Mathematical Olympiad competitors who often become breakout math stars. In fact, she started university at the School of Earth and Space Sciences at Peking University, rather than in mathematics. Her decision to switch from Earth and Space Sciences to mathematics after a year was a turning point. Wang has talked about how the transition was initially difficult. She often struggled, and her grades were not great at first. Peking University was where Wang truly became a researcher. She earned her bachelor's degree from PKU in 2011 after transferring to the School of Mathematical Sciences. At PKU, she realized how different research is from exams. Exams are neat problems with clear answers, meant to be solved quickly. In research, you might spend a long time trying many messy, failed ideas before finding one that works. PKU gave her tough mathematical training, but it never made things feel too easy. She realized she needed strong mental resilience as much as intelligence. She learned this in the dorms and libraries of Beijing, where she changed from a student learning facts to a researcher learning to handle the stress of unsolved problems. After graduating from PKU, Wang went to France, earning a master's from Université Paris-Saclay by 2014. Her time in Paris was full of growth and deep self-doubt. In interviews, Wang shared how she became so unsure about her path in France that she stopped doing mathematics for about 6 months. During this break, she seriously considered switching to architecture. She was interested in how architects use computers and spatial thinking to turn ideas into designs. What brought her back to mathematics was her motto, follow interest and feeling. With her commitment reaffirmed, Wang crossed the Atlantic to begin her doctoral studies at the Massachusetts Institute of Technology in 2014. There, she was paired with Larry Guth, a professor whose mentorship would deeply influence her mathematical style and trajectory. Under Guth, she focused on Fourier analysis and restriction theory, completing her PhD thesis in 2019. Guth taught her the beauty of mathematics. Wang later said he showed her how to think systematically about research and, most importantly, how to develop a sense of mathematical taste. This means knowing which problems are truly deep and which are just hard, and it became her guide. After MIT, her career took off quickly. She held a postdoc at the Institute for Advanced Study in Princeton from 2019 to 2021, then became an assistant professor at UCLA in 2021. By 2023, she joined NYU's Courant Institute, and by 2025 to 26, she held professorships at both NYU and in France. Her research sits at the intersection of Fourier analysis, geometric measure theory, and incidence geometry. Harmonic analysis is the process of breaking complex signals into simple waves using the Fourier transform. For example, it's like taking the mixed sounds of an orchestra and separating them into the individual notes each instrument plays. Since waves are key to sound, images, and quantum physics, harmonic analysis is a foundation for understanding the physical world. The Fourier transform she studies is the same math used in practical applications such as image compression and MRI scans. Geometric measure theory, in contrast, studies how size, shape, and dimension behave for very irregular or jagged sets of points, such as fractals. Wang focused on problems involving tubes, curves, and dimensions because she thinks very spatially. The Kakeya problem is right at the intersection of these fields. The way needles or tubes are arranged in geometric measure theory models how high-frequency waves overlap and interact in harmonic analysis. No mathematician works completely alone, and the story of the 3D Kakeya proof is truly a partnership. Joshua Zahl was that partner. Born in 1986, Zahl earned his bachelor's degree from the California Institute of Technology in 2008, followed by a PhD from UCLA in 2013. His research interests are very similar to Wang's, focusing on harmonic analysis, combinatorics, incidence geometry, and Kakeya-type problems. Great proofs are almost never sudden flashes of inspiration. They are built on the work of many earlier mathematicians. Before the 2025 proof, experts spent decades chipping away at Kakeya step by step. In 1971, Roy Davies successfully solved the two-dimensional case of the Kakeya problem. However, the 3D case remained a stubborn fortress. In 1995, Tom Wolfe achieved a major milestone by proving a lower bound, showing that a 3D Kakeya set must have dimension at least 2.5. In 2014, Nets Katz and Terence Tao developed a strategic roadmap, identifying that any counterexample to the Kakeya conjecture would have to possess a pathological property they called stickiness, where tubes pointing in similar directions clump uncomfortably close together. Concurrently, Larry Guth provided another vital insight, showing that any 3D counterexample would have to be grainy, organized into small 3D chunks. Wang and Zahl used the earlier bounds and translated the problem into families of thin tubes, which provided a basic picture of the rotating needles. The first battlefield was the sticky sets, a victory they claimed in 2022 by proving tubes couldn't clump together pathologically based on their angles. The second battlefield involved dealing with what was left, Guth's grainy sets. A grainy set is made up of tiny, chopped-up sections of tubes, or grains, where a massive number of tubes overlap. Instead of looking at the long tubes, Wang and Zahl zoomed in and analyzed how these microscopic grains could intersect. They created a step-by-step bootstrapping process that is said to be remarkable. They started with Tom Wolfe's earlier bound of 2.5 and used it in their grain overlap equations. The way the grains fit together raised the bound a bit. Then they used this new higher number to repeat the process, raising the bound even more each time. Terence Tao compared this process to a perpetual motion machine because a small geometric improvement could be applied repeatedly until it reached the full 3D dimension. Now that the foundation is secure, the impact on harmonic analysis and partial differential equations is huge. Mathematicians can be confident that wave equations will remain stable without worrying about Kakeya-type problems. Mathematicians often judge a theorem's importance by the new methods it creates, even if there's no immediate product. The grain analysis and projection techniques Wang and Zahl developed are now standard tools. Wang's recent work is already moving toward the Stein restriction conjecture. Pure math usually takes a long time to show its benefits. It won't lead to a new microchip or engine right away. But Kakeya problems are closely connected to Fourier analysis, wave equations, number theory, cryptography, and randomness theory. This proof will lead to the creation of MRI machines, but it also strengthens the theory behind technologies based on waves and signals. Mathematicians care about this work even without instant applications, because understanding the limits of wave interference helps engineers build more stable systems in the future. It's the same thing as inventing a new light bulb versus understanding how light itself works. After the February 2025 Kakeya breakthrough, she collected the Salem Prize, the Ostrowski Prize, and the ICCM Gold Medal of Mathematics. The Association for Women in Mathematics gave her the 2025 Sadowski Prize in Analysis, featuring her trailblazing ideas. At the same time, NYU named her a Silver Professor. This momentum points toward the highest honor in mathematics. The Fields Medal is awarded every 4 years at the International Congress of Mathematicians. It's often called the Nobel of Math because it brings instant, lasting recognition. Recipients must still be under 40 on January 1 of the award year. The next ICM is scheduled for Philadelphia, July 23 to 30, 2026. Wang, born in 1991, easily meets the age eligibility requirement, and the timing in 2026 fits perfectly with the digestion of her proof. On Polymarket, a major prediction platform, the contract for who will win the 2026 Fields Medal, has shown Wang's chances staying between 80% and 87.5% in April 2026. In betting terms, odds of 1/7 show that many people see her as the clear favorite. After Wang, the odds drop sharply. Jacob Zimmerman, known for his work on the Andre-Oort conjecture, is next with a 56% to 75% chance, while Sam Raskin and Jack Thorne are around 48%. Wang has spoken publicly about her relationship with exercise and her love of sports. She makes time to rest, refusing to force math when exhausted, and has engaged in table tennis, fencing, and even online taekwondo. Talking about fencing, she said, "Fencing is an activity which requires different kinds of postures, and these postures must be accurate. Therefore, after I have fenced, I tend to be obsessed with those postures that I have done badly." Importantly, she believes in the value of rest for serious thinking. Her thoughts on procrastination and the value of starting early show that she is practical. Her advice to students is simple: look for those with mental resilience. These details matter because they show how she manages the challenges of difficult work. A mathematician like Wang doesn't stop after reaching one big goal. She looks for the next challenge. Recent reports and conference talks show Wang is already moving beyond Kakeya and working on the Stein restriction conjecture. The restriction problem created by Elias Stein in the 1960s is the next big step. She is now working with Shukun Wu of Indiana University on a geometric approach to the restriction conjecture. Instead of relying exclusively on traditional harmonic analysis, Wang and her collaborators are now making new estimates of how often thin tubes in space cross, using a purely geometric perspective. More generally, her research continues to connect Fourier analysis, geometric measure theory, and incidence geometry. With 4D Kakeya and related restriction problems ahead, it's clear that Hong Wang's story is still unfolding.